In this video, we'll talk about some other types of matrices, as well as the terminology used to describe them, which will be useful going forward when we want to deal with stuff related to what these matrices can do. So the first main type of matrix we want to consider is that of a square matrix. And a square matrix, as you could probably guess, is one where there is the same number of rows and columns. Because as a set of numbers, it's a square. So 2 by 2, 3 by 3, 10 by 10, these are all square matrices. So if we let A be a square matrix, is an n by n square matrix, the entries of the form AII, so row I and column I, are called the diagonal of this matrix. In terms of the actual sort of array of numbers, these are numbers that go from the top left to the bottom right of the matrix along that main diagonal. So for, say, the matrix 3, 1, 0, 0, 2, 1, minus 1, 0, 1, with the 3 by 3 square matrix, the diagonal is 3, 2, 1. These are the entries on the diagonal of this matrix, from top left to bottom right. The other one doesn't mean too much for us, just the top left to bottom right diagonal is what's important. Now, building from this, we say that a matrix is upper triangular if everything below the diagonal is 0. Or another way, if the only non-zero entries are on or above the diagonal. So for this matrix above, this is not upper triangular. For it to be, I would need all of these entries here below the diagonal to be 0. So if I make this minus 1 into a 0, this is now an upper triangular matrix because everything that is below, so down to the left of the diagonal, is 0. You think this is a line down the middle. If you're below that line, must be 0 for it to be an upper triangular matrix. On the flip side, we say a matrix is lower triangular if the opposite is true. That is, if everything above the diagonal is 0, or the only non-zero entries are on or below the diagonal. An example of that would be something like the matrix 1, 2, 5, 0, 3 minus 1, 0, 0 minus 2. Again, everything above the diagonal here is 0, therefore this is a lower triangular matrix. And then our final category is that of a diagonal matrix. And this happens exactly when the only non-zero entries are on the diagonal. This is also equivalent to being both upper and lower triangular. These types of matrices, upper and lower triangular and diagonal, all have really nice properties when I work them to solve systems of equations, and so it's nice to know these in advance, to know what these categories are, because a lot of times we're going to aim for a matrix of this type in order to be able to do something with a system of equations. One more thing to look at before we dive into more of what we can do with matrices is the idea of identity. So we want to find a matrix that behaves like the number 1 does in real numbers. And what's the point of 1 in real numbers? Well, the point of 1 is that if I multiply 1 times any number, or any number times 1, I just get that number back. And so I want to find a matrix that does this same thing for whatever I have going on in my problem. I want to find a matrix that satisfies the property for any matrix A and not just number A. And so for matrices, this is called the identity matrix. And you could figure out ways to like build up what this is, but in terms of how you actually write this matrix, it is a diagonal matrix consisting of all 1s on the diagonal. And it's denoted I sub n for the n by n identity matrix. So for instance, I2, the 2 by 2 identity matrix, is just 1, 0, 0, 1. I3 is 1, 0, 0, 0, 1, 0, 0, 0, 1. Notice these are both upper and lower triangular, and their diagonals are all 1s. Just to show why this is what we say it does, if I take the matrix 1, 3, minus 1, 5, and multiply it by 1, 0, 0, 1, that identity matrix, what am I going to get? Well, for the first row, first column in the product, I'm going to get first row of A times first column of the identity matrix. But since this is a 1 in the first column, it's going to pick out the first entry here and just carry it through to give me a 1. For first row, second column, it'll be first row times second column, and the 1 in the second entry of that column will pick out the 3 to give me a 3 over here. And continuing forward, we'll get a minus 1 from this product and a 5 from this product, giving me minus 1 and 5. The matrix hasn't changed. You can verify this works for any matrix, any product you want to do. It works the exact same way every time. So this here is our identity matrix, and will become sort of our target for a lot of processes or things that we're going to work into problems because it does a lot of nice things with matrices. For instance, it lets us put a scalar into a matrix form. because the number k, in terms of like real number k, really just becomes k times in, and it's now a matrix that I can do things with. This now has k's on the diagonal. Now, the last thing I had to mention here is inverse matrices. So there are a couple properties that we would like to have for matrices that we really don't always have. And the two big ones are listed here. The first is if I have three matrices, A, B, and C, I know that AB equals AC as products, then I cannot guarantee that B equals C, even if A is a non-zero matrix. Right? For real numbers, that is always the case, as long as A is non-zero, right? If I have, for real numbers, A times B equals A times C, then as long as A is non-zero, I can divide both sides by A and get that B equals C. For matrices, that's not the case. Similarly, we have this product too, this zero product rule that we have for real numbers. If A times B is zero as matrices, then it's possible for both A and B to be non-zero. For real numbers, that's not the case, right? This is our normal zero product rule that lets us factor and solve equations. If I know that a product of two numbers is zero, then at least one of them must be zero. For matrices, that does not happen. For instance, I can take the product 1, 0, 0, 0, multiply it by 0, 0, 0, 1, and this will give me the full zero matrix. So that is zero as a matrix, but neither A nor B is the zero matrix. And the main issue with all this is that we can't divide by matrices. We have not talked about division yet. Right? The key step up here was dividing both sides by A. The key step here is assume that A is non-zero, then divide both sides by A, therefore B must be zero. That's how you would prove that. But here, we can't divide by matrices. Or at least, we can't divide by all matrices. So we say that a matrix A is invertible if there's another matrix A inverse, written A to the minus 1, so that if I multiply A times A inverse, or I multiply A inverse times A, I get the identity matrix. So this inverse matrix here, this A inverse, or the inverse matrix, serves as our step for dividing by matrices. So for instance, now if I have this A inverse, and I have that A times B equals A times C, I can multiply both sides on the left by A inverse. A inverse AB equals A inverse AC. Now, since I know multiplication is associative, I can group these together, and both of those become identity matrix. So I get IN times B equals IN times C, but I know that identity matrix doesn't change anything about the matrix itself. That gets me then that B equals C. So if I had this inverse, if I can divide by A, then all this works out great. But that's not necessarily always the case. So a lot we'll be looking at in the future is how do we determine if a matrix is invertible, and if it is, how do we compute this inverse matrix? Because once I can compute these things, I can do a lot of things a lot simpler if I have this matrix inverse on hand and can work with it. That'll be coming in the future, but as of now, just having this idea out there that invertibility is important. Not all non-zero matrices are invertible. For instance, in the example above, both of these two matrices are non-invertible. And so knowing these things exist and they are out there is important as we start doing these matrices to make sure you can't just cancel out matrices from both sides of an equation unless you already know it's invertible first, then you can go ahead with that process. That's something to keep in mind as we move forward, talking about more matrices, what we can do with them in terms of solving systems and doing more analysis of problems using matrices and needing to make sure they are invertible, that they have certain properties to be able to solve equations.